We will now conclude our RTL-to-GDS demo with the final part of our simple SoC example. In this section, we'll go through post-route and SignOff. So let's discuss post-route optimization and SignOff. At this point, we have a fully routed design and we're ready to finish the physical design stage. In the final section of our small SoC demonstration, we'll briefly go over post-route optimizations, including design for manufacturing, better known as DFM, DRC fixing within Innovus, applying ECOs within Innovus, finishing up the design, including fillers, metal fill, design cleanup, sign-off timing, and exporting the design.
So after routing, we are going to run some post-routing timing optimization, and that's run with op-design minus post-route minus setup minus hold. So that's going to do concurrent setup and hold optimizations, timing optimizations, which are already run inside the route op design command, but we can run it again depending on if we want to do all kinds of things. But there are also several options that we can optimize for specifically after routing. So the first one is fixing SI slew violations. Okay, so we might have some coupling that's going to cause problems. So then we're going to set db opt post route fix SI transitions true, and then run our opt design minus post route. Okay. So in general, again, SI glitch violations are going to be fixed by default, but we might want to run this in an opt design if we have specific problems that remain after our initial routing. Now there's also signal EM violations. So these are signal electromigration. That means we have electromigration problems that happen on signal wires, not necessarily on power wires and so forth. And the way we're going to fix them is by widening wires, downsizing drivers, and buffering. And so we run the fix AC limit violations minus allow downsize true, minus allow add buffer true, and then we're going to fix signal EM violations. And we can optimize power. So there's these different ratios for how much we want to fix dynamic power versus leakage power. And we do a set dB design power effort none, low or high, and the opt leakage to dynamic ratio from 0 to 1. And then we would run that. And we can also apply post-route useful skew, which is using the set dB opt skew post-route true option. There are also DFM, or design for manufacturing optimizations, that we can run post-route, and these help us improve our yield. So what are these types of DFMs? Well, the first one is wire optimization. Wire optimization means straightening wires. A straight wire is better manufactured. Widening wires and spreading wires. Wider wires will be manufactured better, and if they're farther away, if there is some sort of defect, it has less chance of hitting mini wires. Okay, so that's three things that we do. So we'd run set db route design detail post route spread wire true, and then do route design minus wire opt, or set db route design detail post route wire widen rule and give the rule name, or route design detail post route wire widen, and then run route design minus wire opt. The second one is via optimization. There are two ways to optimize vias. They kind of contradict each other, so let me explain. The general one that we like to use is multi-cut. That means that we want to use vias that have a lot of vias in them, not just a single via, because if one via is not manufactured well, we have another one in redundancy. Plus, the more vias we have, the better we are for dealing with electromigration and so forth. But there's also via reduction, which seems to be contradictory to multi-cut vias. Well, it's not. It just means that instead of going up and down through metals and therefore having to use a via, if we can go and run a wire just on a single metal, that's better. So getting rid of vias at all, then we don't need a multi-cut via in that place. So those are two things that we want to run. So set db route concurrent minimize via count effort high and route design minus via opt. We'll do this via reduction, or set db route design reserve space for multi-cut true and then route design, and set db route design detail post route swap via true and set db route design with timing driven false, and then route design minus via opt. We'll do this multi-cut via optimization. Again, this is going to do it initially with our initial route design, and this one is going to do it in a post route ECO type of a thing. And there's also lithography-aware routing, so that's to improve our lithography, and that we're going to run already with our route design. Of course, when I write here route design, I mean it's before the route opt design. I'm just showing, the route design is basically the detailed route part of the command. So set db route design detail post route litho repair true, and then route design. So these are three things that are going to help us with our design for manufacturing to improve yield. So really at this stage, I can do my post-routing optimization. So I can opt design minus post-route minus setup minus hold. I don't really need to do that because we saw we don't have any problems at this point. One thing I want to do is wire optimization and via optimization. So I'm going to turn off the timing-driven routing and the SI-driven routing, but put things like post-route wire spread true and use multi-cut via effort high, and then do a route design minus wire opt and minus via opt, and then reset those timing-driven, SI-driven routing. So that I'm going to want to do. They're good for DFM, so I'm going to run those two things. It's now doing post-route via swapping, and it finished the post-route DFM optimizations now. I can also see that it gave a report of how many single cut vias there were. In other words, a via that only has one via in it, or multi-cut where it has more than one via. And I see that a lot of the metal one is really mainly single cut, but on all the other metals, I have almost all multi-cuts, which is a really good thing.
So now let's go into post-route DRC fixing. After routing, there are often DRC violations. So we're going to run the check DRC command after routing. If we run it before routing, then we're going to get all kinds of problems with things because we're just running it on like a trial route or something like that. There are options in the check DRC to only check special route and so forth and so on. But after routing, we can run a full DRC check that is based on our tech left within our tool. Okay, so we're going to often come out and have several DRCs. I can't explain exactly why the tool leaves them over. Sometimes it just is not able to fix them and it runs out of, its trials and so forth. And sometimes there are actual things that are blocking it from being able to finish the design with DRCs. For example, if we placed a cell and it is fixed and the routing step, it causes some sort of DRC. So what we're going to do in general is use ECO routing. So there are several ways to do ECO routing, either with the route design command, however, using the setDB route with ECO true, or with the route ECO, which I guess does something very similar, and we can use the minus fixed DRC option to go and do this ECO routing. So ECOs are when we go and change something after we've kind of finished a stage or all of our design, and so route ECO is gonna, if we go and we put another buffer or something like that, we're gonna run the route ECO. But if we have DRCs and we use the route ECO minus fixed DRCs, it's going to attempt to fix those DRCs that are left over. If that doesn't work, however, we might want to do things like deleting and rerouting the nets with violations. So as I explained in the lecture about routing, there's a lot of heuristics that go on in the routing algorithm. For example, the actual order that we choose to route nets, one net may block another, and so forth and so on. So something that is kind of heuristically works is going and deleting a net that has a violation on it, or a bunch of nets that have violations on them, and try to reroute that area. So we can go and check the DRCs. We get, the tool knows now what DRCs we have inside. Then we can go delete routes minus regular wire with DRC, and that's going to go and just remove the routes that have, the wires that have already been routed during the route design command. So if we do that delete route, it's not going to delete all the routes in the design, just the ones that have DRCs on them. And then route design again is going to route them. Okay, you can also do this manually, like grab a bunch of routes in a certain area, hit the delete button and then do an ECO route. To save runtime, you can try routing only selected nets. So you can do setDB, route selected net only true, select the nets that you want to reroute, and then do a route design and see if that helped. Okay. Sometimes we have these gaps, notches, and hole geometries, and there are different commands such as delete notch fill will go over and find these little notches and fills and holes and stuff like that are left over from the whole routing process. So it will do a scan of all over the design and try to delete them. Another thing is dangling wires, so you can remove or trim dangling wires. So sometimes we have a wire that just has a piece of it that we don't really need over there. So edit, trim routes will go and remove that type of a thing. So just as an example, there's a little picture here. So this net was routed and then this net was routed, and actually nothing is done with this piece of net 1. So we can go and delete it, and maybe it will alleviate some sort of a DRC that we have. DRC violations that you only see in your SignOff tool, you can actually import your DRCs from an external tool with the read markers minus rule map file and the type from PVS, from Calibre, and so forth, and then route fix SignOff DRC.
Okay, so that was our routed design, and our design really has all this routing already done. And let's look at our DRCs. So my DRC is going to run a little bit longer maybe now because I have my detailed routing. And when it finished, I see that I do have one violation on middle 1. So I'll go over to the violation browser, and I see that there's a short on middle 1. And let's see, this is a short over here. And why do we have this? Well, first of all, this is a tie cell, okay, which was placed over there. And it probably was just placed in a really bad position that caused a short over here. Let's see, what do we see over here? Actually, the Y pin looks like it's too close here to something or something like that. So I'm not sure exactly why that is. There are many ways that we can fix things. So really we can do all kinds of things like rip up and reroute. So I can go over here to nanoroute, okay, and I can look at this type of thing, and I can do area route. Select the area, right? I can go with my mouse and select this area and say I want to rip that up. So let's go back to the nanoroute thing. So it selected the area. I select area and route. Okay, so and I will, well, I guess I select that area, and we hope that maybe it will fix it. A lot of times, for some reason, that does work. So this is going to take a few seconds or minutes, and it didn't seem like it fixed anything. What I think is that there is a problem here with how we actually placed this tie cell. We didn't go and place it by hand. It was placed there automatically. So let's just grab it and move it. Okay, so we moved it over there. And let's go and now reroute this entire area, again, with the same way we did it before. So route, nanoroute, let's try and see if that'll work. So I'm going to, again, do some ECO route, area route, and I'm going to select area and route, and select this whole area, and let's see it reroute, and maybe it'll fix my problem. Okay, and what do I see? It did make a change over here. So we see that it really changed this area, and let's now do a check DRC on that. I could have checked just the area. I didn't have to actually run a check on the whole DRC. And look at that. There are 0 violations, and it went away. You see that there are no more violations. So I showed you a few simple ways of fixing DRCs. One of them was really there was a problem here with the place that we placed the standard cell, and it was fixed, and it didn't want to move it. So that caused the problem, and I just moved this tie cell a little bit. It didn't probably make any difference in the design at all, and I was able to reroute the area and fix the problem. But there are some commands that I can use. So I can do things like delete routes, regular wire with DRC, and then route the design or route ECO. I can't tell you exactly what the difference is between them, but it will reroute the wires that we deleted, and hopefully it will do a better job at doing them without DRCs. I can just do route ECO minus fix DRC. It will go over the wires that have DRCs on them and try to fix them. There are other types of different DRCs we may see. So delete notch fill, fix DRC routing min step. There are different types of options that we can run and try to do things. You can just go and grab a wire, delete it manually, move around some instances, and try to see if that helps fixing what didn't work before.
So the next thing I just want to really briefly go over is applying ECOs. This is actually a big flow within Innovus and Tempus and all kinds of other things. But ECOs, which is a strange acronym for engineering change order, which means that we're going to go and do small modifications at the design at a very late stage. Often this could be, post-route. It could be post-placement if like a placement or a clock tree took a long time and we don't want to go and rerun everything. But it's often done at a post-route stage. We usually apply these things in two cases. One is after routing a large design, and that's just to save time for rerunning the whole flow. Because if we have a really large design, it can take days literally to finish a whole, synthesis to post-route flow. And even just the routing itself can take many hours, maybe even days. So instead of going and rerouting the whole design, we can do these little fixes if we find something that we need to do. Okay, and the other thing is a metal fix after tape out. So when we tape out the design, there's actually several, weeks usually until they tape out, until they actually go and manufacture the back end layers. So you can actually send a metal fix, which means that we just change back end layers and we don't change front end layers several weeks after the tape out. It can also be a respin of a design where we only change the metal layers, and that saves a lot of time and money in the fabrication itself. So ECOs can be implemented automatically, like there's the Tempus ECO flow that I mentioned before, or they can be applied manually. And so we would be turning off the automatic ECO, setDB ECO refine place false, setDB ECO update timing false, and then manually add a buffer. For example, that's a common ECO type fix. So ECO add buffer, we choose a cell from the library, which net we want to connect it to, and what the coordinates we want to put it at. That will add a buffer manually into the design. And we can do this with all kinds of other cells and so forth and so on. We can do something like upsize or downsize the cell. So ECO update cell, give the instance name and say minus upsize or minus downsize. And we can manually change the cell, ECO update cells. We take the instance and we say we want to put a different library cell there. And after we do this, of course, we have to run placement legalization. So running the place detail will legalize the placement of the thing, and then we should run a route ECO to fix the routing as well. So this is just a real small taste of what we can do with manual ECOs. Again, there's a Tempus ECO flow. We'll take our timing from Tempus and provide us with a script that we can bring into Innovus and run our ECOs. And the tool will also do a lot of things by itself. So next we're going to go over to finishing the design. And we need to clean things up really at the end. So that includes, first of all, adding fillers. So remember that we had lower than 100% utilization, which means we have all these holes in our design, like places where there are no standard cells. And so we use the add fillers command, and there are all kinds of options of how to add fillers, which fillers to add, and so forth and so on. But they kind of fill in all of the missing N wells and P plus and N plus and P active areas, and just all kinds of things that are missing, maybe some density type of stuff that should be down there. Okay, alternatively to just regular filler cells that are nothing but a filler, we can add decap cells. Decap cells will add capacitance between VDD and ground to help and clean out our the noise on the rails, or in other words, improve our DI to DT drops and so forth and so on. So we want to have as much capacitance between VDD and ground to have as strong a power as possible to have some little wells there to provide us with charge when we're doing all kinds of transitions. So you can do that with add decap cell candidate. You give the name of a decap cell, and then you use the add decaps to add the decap cells. Okay, you can also add and check metal fill with an Innovus. Sometimes this does not work good enough for sign-off, and then you need to use an external tool such as Caliber or Pegasus or other ones that have a run set for DRC fill, but for metal fill. But you can also try with Innovus. So it's something like this: add metal fill minus net VDD. That will connect the metal fill, the dummy fill, to VDD, and then running the check metal density will run density checks. Again, this is not sign-off level, but it can really help, especially with the fact that in modern processes, metal fill can, due to the coupling capacitance, can affect the timing, and Innovus is aware of that, where a standalone DRC tool is not aware of the timing effects of that, and it can really cause trouble that we'll need to then apply other ECOs. Okay, we may need to fix timing violations, as I just said, so you can do something like trim metal fill near net minus slack threshold, minus min trim density, minus spacing, and so forth, that can help you fix some of the timing violations that you had with metal fill. There are all kinds of ways to do this and lots of commands, and you have to play around with them and see what works. Okay, and there's all kinds of things that can be left over in our net list at some point during our place and route flow. So we have these commands that can be run again at different places. They can be run really early when we import our design and so forth, but you may need to use them really in order to clean things up and pass LVS and so forth. So delete assigns will get rid of any leftover assigns. That will put a buffer instead of an assign, for example, from an input port just to another net. And so you can't have these assigns when you're running LVS. Sometimes though the tools will leave them in, so it will put a buffer instead of them. Delete empty agents. So sometimes you have these hierarchical instances that in the end they for some reason get synthesized away or something, and they're just empty sitting there and messing up our design, and again causing problems potentially with like our LVS flow. Delete dangling ports, same thing. We may have some sort of a port that's left over there for some reason. And delete floating constants as well. We may have some sort of constant that stuff down the line just kind of got synthesized away, and they're left over there. So these are commands that they're kind of trivial sounding, but again, things get left over, and if you don't run the commands and tell the tool to do it, then they'll just be there at the end of our flow.
So now we are ready to start the sign-off stage. So I'm going to start sign-off. And the first thing I'm going to do is to add fillers. So let's go into our design over here. And I notice that there is basically nothing in all of these areas, and we need to fill it up with fillers. But even in the standard cell placement areas, there are these empty spaces that need to be filled up with fillers. So everything should be filled with filler cells for various reasons. So I set up in my setDB all kinds of options for that, and then I'm just going to run the add fillers command. Okay, and the add fillers command is going to run now, and it added quite a lot of fillers, and it added them. I start with the big fillers like that are very wide and see what happens. So let's see what that did actually over here. So now I see that I have fillers everywhere in my design, all of these fills over here. If I look at my whole design now is covered with fillers all over the place. I have very wide ones here in these empty spaces, which is most of my design is pretty empty. Okay, so now I have to actually check that I didn't cause any DRC violations. So we're going to fix DRCs after adding fillers. So I will check DRCs. Okay, so it did cause all kinds of DRCs. So let's go and see what they are. And I see that there are these, okay, so I have the opens from the verify connectivity, from the check connectivity, but then I have this metal 1 end of line spacing. So let's try to understand what that is. So it doesn't like that for some reason. Okay, let's see what else it does. There's this metal 1 short in different places. So it caused a short over here due to these guys for some reason, that it did something there. Okay, and what else do we have here? We have parallel, I mean, we can see those are all over this pin over here, and it's the pin that's on the side here of one of the SRAMs. So there are all of those, right? And we also see that there's a parallel run length. So these guys have some parallel run length problems as well over here. I have a feeling that I'm going to have to somehow fix this up over here. Adding fillers caused some sort of problem. Maybe it's just because how the SRAM was defined relative to the site of the design. Okay, so what am I going to do? Well, first of all, what I will try to do is add fillers minus fix DRCs and see if that helps. So it does not look like it helped very much, but let's look and try to see. So let's go back here. Did it change anything? It sure doesn't look to me like anything was changed over here. Let's see what we have now. So I will route ECOs and fix DRCs and see if that helps. So it still is telling me during this that I have 2 problems, and it's continuing to try and fix them. It finished saying that there are 0 DRC violations. Let's just open up our design again. And did it change anything actually over here? It sure doesn't look like it. So I'm guessing that this is still going to be a problem. Let's run check DRC again. And it indeed did not fix anything. Okay, so I'm not exactly sure why. Let's see what we have over here, by the way. So we have this VDD and ground connection that was kind of painful over here. We could try to do something like erase all of it and just hope for the best of what happens. Let's see if I delete these guys and do something like trim dangling wires. Let's see what that's going to do. Because if I do get rid of those, it probably shouldn't give me any trouble. So I'm going to go and see if that worked. So I want to save some time, so I'm going to go check DRC and then specify the area. So I can go and draw a specific area, the view area. So let's do the view area and then do apply. And let's see what it says. And it says that there are no violations. So that's a good thing. Maybe my approach actually did work there before. What is this violation actually? So that's an antenna violation for some reason. Well, anyway, we're going to go over here and do the same thing. So this is because of these strange connections over here. So I think I'm going to just erase them because they shouldn't really be causing me any problems. So I'm going to go erase them along the sides here. Let's zoom out a bit. So I think I can erase that one. And I can erase that one. But this is the type of thing you have to do to fix these violations without causing any trouble. Sometimes we could have actually added fillers at the floor plan level and see if this was going to cause trouble. Let's see if we have anything else that's over here lit up. There's X's over there. I can't tell exactly what they are right now. They might be what I already erased. And I see something over here. So I have a similar situation over there. Usually if I just erase some sort of one power pin, is not going to cause me many problems. Of course, you should do IR analysis to check that out. Anyway, this is just a funky design over here. So then I'm going to go and trim those wires. I'm going to go and I'm going to route ECO, let that run. Okay, and after that I'm going to again check DRC, and I better do it on my whole design over here, which takes quite a while. And voila, I don't have any DRCs left, so that's a really good thing. I better check connectivity though, and see that I didn't screw anything up. And I have my 8 problems that I had before, so really in my violation browser I only have those. So I fixed my problems. How I did it, it was a bit lucky and a little bit of experience, but really playing around with those types of kind of route ECO, fix DRC, route ECO, edit trims, trim dangling wires, those types of things tend to help. So I added a couple more commands here. Delete assigns. So there may be assigns for some reason somewhere and we have to get rid of them. So I run that because it will cause me trouble with LVS afterwards, but probably not. And empty hierarchical instances. So it's just doing that.
So now we're going to discuss very briefly sign-off timing. Okay, so for sign-off timing, we have op sign-off and time design sign-off. So op sign-off with meet minus DRV minus setup and minus hold. That's just another type of an op design similar to the one at post route, but it's kind of more careful in what it actually does, and it's just improving things like the DRV violations and maybe some setup and hold violations. And time design sign-off is going to actually go and invoke the Tempus tool for running this. So you'll need licenses to Tempus and have it set up to go and run Tempus within Innovus. And that's like a sign-off level timing tool. So when I run Tempus, I'm going to run, this sign-off timing, and advanced timing analysis modes should be used that I discussed a bit in the lecture. And it's really a bit complex and beyond the scope of this tutorial, but there are several things that I just want to mention briefly. So the first one is on-chip variation. On-chip variation is this thing that we started to take into account many years ago, and we understood that within die variation is a huge problem. You can have a buffer on one end of the chip and one on the other end of the chip, and they'll have very different, delay and so forth because the operating conditions are different there. We'll have a different temperature across the chip. We'll have different IR drop across the chip. Even maybe things that happen due to process variation during manufacturing will be different. And it doesn't necessarily have to be, two buffers that are far away from each other, two gates that are far away from each other. It can be in different places and so forth. So when on-chip variation was introduced, what basically was the methodology was to set a timing derate. And what the timing derate does, and again, methodologically, you can implement it in several ways. You put a multiplier across the delays on your data path and your clock path. So basically your launch path, for example, in setup, you want to make setup worst case, so you'll make it slower. So you'll multiply the delay by some sort of factor, like increase the delay by 10% on the delay path. And on the contrary, you'll want to make it harder by making the clock faster. So you'll multiply by 0.9 or something. You'll make the clock path 10% slower, and that gives us kind of a really hard case to meet timing. And on hold, you'll do the opposite. You'll make the clock path slower and the data path faster. So that is what is we call OCV, and that's separate from the regular kind of timing that we've been discussing, which is called best case, worst case, where we just check setup and hold regularly. In fact, so set timing derate is usually the command that you apply to implement OCV, but you have to also add the setDB timing analysis type OCV to have the tool take this into account. In fact, when you do this in Innovus, put this OCV on, even if you don't apply timing derate, what it's going to do is going to use the worst case libraries for your data and clock path. So it's going to use the, for example, in setup, it's going to use a bad corner, like a slow corner for your libraries, actually the timing libraries of the cells for your launch path, and a fast corner for your data path. It isn't actually that clear from the manuals, but I think that if you do add the timing derate, it will override that, and they won't do the two of them together. Okay, but there's this situation where you actually have the clock is kind of shared usually between the launch and the capture flip-flop for a certain part of our path. So we have our PLL or whatever that's creating our clock, and the clock propagates until some point where it branches off, and one branch goes to the launch flop and one branch goes to the capture flop. And it's kind of ridiculous to go and put these timing derates on that shared part of the clock, and that's what is called clock path pessimism removal, or CPPR, which goes and it finds that place where the clock branches off to the two, and it removes that from the derates. So you do that with setDB timing analysis, CPPR, both. Okay, but on-chip variation was very extreme. Like a brute force applied this derate to the entire, data path and clock path and so forth, and it became hard to meet timing. So they came up with this advanced AOCV, which wanted to put in two different types of things. One is to see that if we have a longer path, it can't be that all of the gates on the path are actually, in the worst case. It's due to all kinds of randomness. So what AOCV did, it brought in these lib files that have tables that say, depending on the kind of length of the path, we are going to remove some of that pessimism and create the derate factors on the fly according to the length of the path itself. That is AOCV. The other thing that AOCV enabled was some sort of spatial derating. So if you have one flop or one gate on one side of the chip and the other gate on the other side of the chip, then obviously there's a good chance there's going to be high OCV. But if they're right next to each other, and they're close to each other, then probably they're not going to be that different from each other. So if you provide some physical locations for the cells and so forth, AOCV can also remove pessimism for smaller areas. And so that is done with SetDB timing analysis AOCV true. Okay, but that was also found to be an overkill and not good enough, and they want to remove more pessimism, and that is where statistical timing analysis came up. So first, Cadence came out with this SOCV or statistical OCV, and Synopsys came out with POCV, parametric OCV, and they kind of, there is no current standard as far as I understand, but at some point the Liberty Foundation or whoever makes these Liberty files, lib files, came up with a new format called LVF that puts some of this statistical aware type of timing information inside one file. So nowadays what we're going to do is we're going to actually have our lib files in this with this LVF information that gives us the actual distribution of how the delays go inside our different timing files. And then we're going to add a side file, which is the statistical or parametric OCV, which is going to give some additional information, including the spatial information. And we do this with setDB timing analysis SOCV true in the Cadence tools. Set timing derate, it takes in the sigma and the mean of the LVF files and so forth. Instead of just multiplying everything by a standard factor, it's going to do it according to some sort of a statistical probability. To do all of this, we actually need to tell the tools where to find these files and so forth. And for that, we need to define the AOCV or the SOCV and the MMMC. So in our create library set inside our MMMC file, we're going to give LVF lib files. So these are files that are provided by our foundry or that we characterize ourselves that are going to have this LVF information, and these side files for AOCV or SOCV, depending on which one we want to use, we can use it. You can also take an AOCV file and have the tool automatically create the SOCV information, but it's better to have an actual SOCV file that is used. Anyway, this is quite complex, and it's in the setup of Tempus usually when we do our sign-off timing. So once everything is finished within Innovus, it's really time to export the design. And there are lots of files that we want to export to go on. So the first one, I guess, would be write netlist, and this exports the Verilog netlist of the design, creates our .v file that we can go and take to our LVS and to our gate level simulation and so forth and so on. Write def is going to export a def file. A def file is a design exchange format, I believe is the acronym. And it has everything about the design in it. It can be at the floor plan level. We can save our floor plan information over there. After placement, it can provide the standard cell placement. And after routing, it can actually provide the entire kind of design that we have here. So you can go and load it into a different tool and recreate our design. Write left abstract is to generate an abstract, the left of the current block. So if this is a block that we want to go and use as a hierarchical kind of a macro, then we want to create an abstract to be able to load it into a higher layer. So this is going to create a left similar to the abstract generator that maybe you've run in a custom design tool like Virtuoso. Okay, write timing model builds a lib file of the top level. So it's the compatriot of the left file. We need a left and a lib to go in and use this hierarchically, unless we do something like an ILM flow. So this is how we create a left and a lib with write left abstract, write timing model. Write timing model is a bit more complex. There's a lot of options within the command. Write stream is an export of the GDS, the layout, so that's what we need to do, our tape out and to do an LVS. GDS is called a stream file, so write stream is the command to export a GDS file. Write DB, it exports the design database in the native Innovus DB format, and that enables us to go and load our design back into Innovus or Genus or the different tools. Write SDF exports delays to a standard delay format file, so that enables us to run some sort of external timing file, which tells us, the different cells and what their delays are going through them. And write design is a command which I am not sure why it still exists and if they are not going to replace it entirely with WriteDB. But export's designed for loading in Tempus. I assume that at least eventually, when we'll be able to load DBs into Tempus, that is, this common UI is supposed to have all the tools load the same thing. But currently, at the current versions, write design exports a design for loading into Tempus in a bit of a different format. And finally, we have this kind of a write do lec, which creates a do file for conformal lec, so we can run our logic equivalence check using the Cadence tool.
And then I can export my design. So I will run that. The export design does all kinds of things. It exports a whole bunch of things. So I added the -netlist -sdf options, and we'll look at that in a sec. So under the scripts procedures, we have EnICS export design. It has all these options: Unicify, left, GDS, LVS, netlist, def, spef, SDF, ILM, libs. So we have all of those. And so what it's going to do, basically, it's going to, depending on which options we chose, it's going to extract the different parts. For example, when I do -left, it will write an abstract that I can then use for integrating this block as a hierarchical block in a bigger design. GDS will stream out a GDS file. I will have to have the GDS files of the different leaf cells to get something that's good, at least. Netlist, there are two types of netlist. There's a regular netlist for gate level simulation, or there's a netlist for LVS, which will have physical cells. It will get rid of the leaf cells and flatten buses and all kinds of other types of things that will help me run LVS. There is a def, that is another way of abstracting things away, similar to a GDS, I guess. Spef is the parasitics of the design. SDF, we saw before, is the standard delay format, so it helps us show the delays. ILM will make an ILM for hierarchically integrating this into a higher block. And lib will create a lib file, so you can either use an ILM flow or a lib-left flow for integrating this block into a full chip, like a higher level design. Of course, when we have this design was an entire chip with the pad ring and stuff, so that is not relevant, and that's why in our command we only exported a regular netlist for right now, and in SDF we're not going to be running LVS during this example. Okay, in the meantime, that finished our EnICS export design, and we can end the stage, which will create our sign-off reports. And with that, basically, we are finished with running our design.
So to finish up and summarize this entire lecture series, we showed in this final section how to implement a simple but actually full SoC from RTL to GDS. We started by introducing the SoC architecture, and we showed that the provided RTL can run a full high-level language compilation tool using C. We can write a C program and really compile it down and load it onto the processor there, onto the SoC, and run a program. Okay, we explored the SoC, we looked at what types of parts it has, and we looked at things that we hadn't seen in the previous parts of the tutorial, which included instantiated hard macros like SRAMs and IOs. Okay, then we ran full chip synthesis with Genus. We moved the design over to Innovus for physical implementation. We created a full chip floor plan, which included macro placement and the IO ring. We ran standard cell placement on this full SoC. We synthesized the clock tree. We routed the design. We fixed DRCs. And finally, we examined the timing reports and saw that we meet all our timing expectations. We finished the design, cleaned things up, and exported our final files, ready for sign-off. So this was a simple example. We ran it in a mature process node, but it really included the majority of what goes on in a large design and an advanced process. So I think it gives you a good picture of what you need to do in a complete chip backend flow. And I hope this was enjoyable and you learned a lot from it. Thanks a lot.